Hello, everyone. Welcome to today's webinar. My name is Jiyoon Kang from MIDAS IT. In today's webinar, we will talk about some of our updated features, especially about moving node analysis according to Australian standards, which is AS 5100. And we have lots of updates feature in 2020 version 3.1. If you'd like to see our updated feature, you can visit our website. And if you go to this About Us tab, and if you go to this news menu, you could download release note here. Here are some updated features list, and today we will talk about this moving of the features according to AS code. Okay. So the features that we are talking about today will be only available from MIDAS 2020 version 3.1. Let's get started. So before we dive into our updated features, there might be some people who never used moving load analysis using MIDAS. So I will show you how you can define moving load analysis very quickly, and then we start over from road traffic functions. Okay. So firstly, how we use moving load analysis is this is menu in MIDAS. If you go to load menu and if you select moving load type, then you could find this menu. So we have three steps here. First one is defining traffic lane. So once we have traffic lane, and then we'll define vehicles, and then in moving load case function, we decide which vehicle applies to which lanes. I'll show you very quickly using MIDAS. So I have this example model. So as I mentioned in the slide, if you go to load menu and moving load type, then we could find this menu. So first step, we can define traffic lane. I already defined some of lanes here. So you can just select the start point and end point, then you get these traffic lane. So we have here 1, 2, 3, 4, 5 lanes here. And then second step is defining the vehicles. If you go to add standard menu, we have our vehicles in the database. You can also define your own vehicle manually using add user defined function. And then we have just 5 lanes, and we have a number of vehicles here. And lastly, in the last step, we can decide like this, which vehicle apply to which lanes, and number of loaded lane. If we input 5 here, then the M1600 will be applied to all of this lane. And as I input a 0 value as minimum number of loaded lane, it will consider when this vehicle applied to 0 lane and 1 lane and 2 lane and 3 lane and so on, up to 5 lane. So it considers all the cases and gives you minimum and maximum results. Okay, this is simply how to define how to use moving load analysis. And after having moving load analysis cases, then we could see the result. Simply, when we have a model, analysis model, we can check on the result menu, we can check result, deformations, forces, diagrams, and stresses, and so on. So here, if you use moving load analysis, you will see only the envelope result. All of these results are maximum or minimum results. But sometimes we need to see, we would like to see where the vehicle is located when it shows maximum or minimum result. Then we can go to moving tracer function. And if you input the key element, if you select key element, element number 350 is here. So for this element, for the maximum bending moment, the vehicle should be located in this area. So you can check the critical location of the vehicles using moving tracer. And if you use this right min max load to fire button, you can convert this location of the vehicle to a static loading as well. Then you could see concurrent forces as a result, so on. We will talk about in more detail later on. So that's it about simply how to use moving load analysis function. So we have actually another webinar which describe how to use moving load analysis in very detail. You can watch it later on. Today I will talk about Australian standards 5100.2 and 7. So when you have a look at the design code, especially for beginner engineers, it is sometimes hard to check everything and apply to analysis model. We need to understand every single classes, right? Firstly, when you have a look at AS 5100.2 and class number 7.2.4, then it says about for the M1600, we have variable spacing, and it shall be determined such as to produce the most adverse effect. So this spacing between these axis group can be minimum 6.25 meter to infinite. It doesn't specify about the maximum spacing, so it can be 8 meters or 15 meters and so on. So how we consider this in analysis model, so I'll show you that. So this is the screenshot of moving tracer function. It is showing the critical location of the vehicle here for this key element for the bending moment. And we have another beautiful function here, says detailed result. If you click on here, this window will pops up, and it is showing the variable length, which means variable spacing between the axis group here. So this value. So it is considering the minimum value, which is 6.25. So when you define the vehicle, when you define M1600 vehicle, it says number 6 and 7, it is a minimum 6.25 and maximum infinite. So it can be 100 meter or 50 meters, 8 meters, 6.25 meters. So whatever the spacing is, the software, the MIDAS server will find the critical spacing to produce the most adverse effect as specified in Australian standard. And next, we move on to next. In the same class number, it says M1600 load shall be positioned laterally within a 3.2 meter standard design lane. So how we input, where we input this to analysis model. So in the first step, as I mentioned, defining traffic lane is the first step to use moving load analysis. So when you define traffic lane, here you can input 3.2 meters for lane width. And additionally, we can define wheel spacing. I have just copied some descriptions from our online manual. It says wheel spacing is the spacing between the wheels. Of course, for influence line analysis, the program MIDAS automatically applies a load equals to a load value divided by the number of wheels to each wheels. Okay, and basically the vehicle will be applied to the center line of the traffic lane, but especially when it comes to curved bridge, we need to consider some additional location in the transverse direction. So if you check on here, a transverse lane optimization, not only center line of the traffic lane, the vehicle will be applied to left end and right end of the traffic lane as well. So we have two additional locations in the transverse direction. And MIDAS will automatically compare all the cases and gives you only one the critical case. So it can be left end or right end or at the middle. Okay, so this is additional option. So if it is very simply straight bridge, you don't need to consider about this, I think. And move on to next. I'm trying to explain all the things very quickly because we have lots of features updated in version 2020, version 0.1. So we will record this webinar and upload it to our website. You can watch it later on again. Let me continue. So another thing we need to consider is that M1600 moving load should be continuous or discontinuous, and of any length as may be necessary to produce the most adverse effect. Again, the uniformly distributed component of the M1600 can be continuous or discontinuous. So we need to find which case will show you the maximum or minimum result. Again, MIDAS will do that automatically without any inputting the value to any option. So, like I said, to use moving load analysis, the first one is we need to have this lane. This is example model. And then as a result, if we select key element, it will draw the influence line analysis diagram, and it shows the critical location of the vehicle. So it is showing discontinuous because for this element to have a maximum bending moment, it must be discontinuous. If you apply uniformly distributed load to all the overall length of the bridge in the longitudinal direction, you won't be the maximum result. Okay, so it will do that automatically. Move on to next. In the same clause, so we have this table about dynamic load allowance factor. So as you can see here, for different vehicle type, we have different value. So we need to apply different dynamic load allowance factor to each vehicle type. So where we input this value in MIDAS. So in the process of defining moving load analysis, in the second step, we will define the vehicle. And when we define the vehicle, we can input dynamic load allowance factor. So if you use our database vehicle, if you select M1600, for example, the default value is 0.3 as specified in the code. And if you select M1600 3-axis group, the default value is showing 0.35. And you can also manually modify the value here. So these are actually same vehicle representing M1600, but we separated it because when we apply a 3-axis group of M1600, we need to apply different dynamic load allowance factor. That's why we additionally updated this vehicle. Okay. In fact, M1600 and S1600 is already implemented in the previous version as well. Later on, after these vehicles, I'll talk about the new vehicles as well. So don't worry about it. So we have also S1600. It says similar description. So uniformly distributed over the width of 3.2 meter standard design lane. So we need to have 3.2 meter width design lane. It is very similar, and it also can be continuous or discontinuous to produce the most adverse effect. And also the axis group, load position, and variable spacing shall be determined such as to produce the most adverse effect as well. So it is very same with M1600. So we have same capability for S1600 vehicle as well. So I'll skip that point. So when you define S1600 vehicle, it is also considered minimum 6.25 meter to infinite spacing. So finally, we reached to heavy load platform. Many of Australian engineers was waiting for this vehicle to be updated in MIDAS, so we updated it. So we have HLP 320 and 400 in Australian standard. So we updated both of them. So all the conditions are same for both vehicle, but the only one difference is having a different axle load value. Okay. So when you have a look at the clause number 7.3, it says the vehicles, the heavy load platform shall be positioned within 2 standard design lane. Not like this is something different from other SM1600 vehicles. So we need to have at least 2 standard lane, then and heavy load platform will be positioned within the 2 lanes. And it can be positioned up to 1 meter laterally from the center of 2 standard design lane. So we exactly, in the same way, we updated our this vehicle to MIDAS. And we need to find the most critical location in the transverse direction as well for heavy load platform. And the half of either M1600 vehicle or S1600 vehicle can be applied together. And at in this case, we don't apply lane factor for S1600 and M1600. We are considering this as well. So after defining traffic lane and the vehicle, when we define moving load case, we need to select heavy load platform option under select load model. And then we can choose here heavy load vehicle and then we can select either M1600 or S1600 here. Then it will be those will be applied together, or you can leave it as blank for this M1600 or S1600. So you can apply only heavy load platform. Anyway, in this example, I have 5 traffic lane here, and then I assigned lane 4 and 5 for heavy load platform 320. Then this vehicle is plotting within these 2 lane, and the software gives you the most critical transverse location. Okay, and lane scale factor is applied to SM vehicle as 0.5 as specified in Australian standard. And move on to the class number 7.6. This is accompanying lane factors. If more than 1 lane is loaded, whatever the vehicle is, we need to multiply the additional lanes should be multiplied by this lane factor as given in the table number 7.6. So when only 1 lane is loaded, we don't need to care about this lane factor. But let's say when we have 2 lanes, the most critical lane will have 1 as a lane factor, and second critical lane will have 0.8 as lane factor. When we have 3 or more lanes loaded, secondly, critical lane will have 0.8 as lane factor, and 3 or more lanes will have 0.4 as lane factor. So we need to find which is the most critical, which is the second critical lane, and which is third critical lane, and apply appropriate lane factor to each lane. Again, this is same example model. We have 5 lane, and we apply lane factor to different option. So it says the first, the most critical lane, we will apply 1 as lane factor, and for the second critical lane, we will apply 0.8, and 3 or more lanes, we will apply 0.4 as lane factor. This is actually not scale factor, it's lane factor. We use same dialog for other design codes, so we just use same expression here. Anyway, this is lane factor. You can manually modify the value as well. So after having moving tracer as an analysis result, again, if you go to detail report button, then we will have this text window, and it says for each lane, we apply, the software applied which lane factor. So lane number 1 is the most critical lane, so it applied 1 as lane factor, and lane number 5 is the second critical lane, so it applied 0.8 as lane factor. And it shows also in the second line, it says variable spacing value for each lane as well. As you can see, different lane has different spacing of M1600 vehicle. Okay, move on to next. Again, about dynamic load allowance factor. It applies to both the ULS and SLS load combination. And the design action is equal to 1 plus alpha multiply times the load factor times the action under consideration. And I will show you how we considered in MIDAS survey for different vehicles. So we have under vehicle definition window, we have W80 and M1600, S1600, and A160 and heavy load platform. For a different vehicle, we need to apply appropriate dynamic load allowance factor, proper value of dynamic load allowance according to Australian standard. And we additionally updated horizontal forces function as well. We have this function for Eurocode and ASH2 and other design codes already. And from the version 2020 3.1, we updated horizontal forces feature for Australian engineers. Anyway, in this 7.8 clause, it says the bridge shall be designed to resist the most adverse coexisting effects induced by the M1600 moving traffic load and the centrifugal force and the centrifugal force. So we need to calculate the value of centrifugal forces and then apply to analysis model, and we need to consider it when we design the bridge. So this is how to apply centrifugal forces in MIDAS civil. So after performing analysis, as I mentioned, we have moving tracer function, and here we have write min-max load to file button here. If you click on this, this window will pop up, will show up, and then you can check on centrifugal forces option and input the height of forces from deck level and design speed of the vehicle. And when it comes to curved bridge, we need to input radius of curve, and also we can consider shift elevation value to the calculation, to the formula, and we need to decide the direction of the centrifugal forces. If you click OK button, then this another text formatted data will show up, and we can copy all of this text and go to the menu, tools menu, and mst command shell and paste it and run. Then we will have additional static load for centrifugal forces. We can generate additional static load of centrifugal forces automatically. So this is how to get centrifugal forces using MIDAS civil. Okay, and when it comes to curved bridge, we need to select the option to decide the direction of centrifugal forces. So let's say the direction of the vehicle is this way, from left to right way. And when we click left to right direction and click OK, then you create this static load case for centrifugal forces having this loading direction. If you click on right to left direction, the direction will be opposite. Okay, so direction of the vehicles can be defined when you define the traffic lane. You can select moving direction, and forward direction is set in order to in order of the element input when you define the traffic lane. And we have another horizontal force, which is braking forces in the class number 7.8.2. So we need to make this calculation to create braking forces manually before, but we have this longitudinal force option in moving tracer when you convert moving tracer to static load. If you click on that, you create additional static load. So if you check on braking force option, then you generate this static load the direction to be the same as loading direction. And we have additionally added traction forces as well, which is opposite direction to braking forces. Okay. So if you don't like to have a traction force, then you can just simply check off here. Moving on to next, in the clause number 7.9, this is fatigue load effect. So it says the fatigue design traffic load effect shall be determined from 70% of the effects of a single A160 axle or 70% of a single M1600 moving traffic load without UDR. So we need to apply a single M1600 having 70% effect. So how we do that in MIDAS? So when we define the vehicle, for example, for A160 vehicle, we can check on fatigue option, and then after having vehicle and traffic lane, when we define moving of the case for A160 vehicle, we can select fatigue load model here. Then it will apply 70% effect to the vehicle. So we can check in the analysis result. So let's see how MIDAS will consider fatigue load effect. So when we see moving load tracer, this is the example analysis result of A160 vehicle, which is having 160 kilonewton as axle loading. So 160 kilonewton times 0.7 as fatigue load effect equals to 112 kilonewton. If we divide by 2 axle, then it shows 58 kilonewton for each axle in the transverse direction. But it doesn't show the value including dynamic load allowance value. Actually, we applied 1.4 as dynamic load allowance factor, but it doesn't apply it to this value in moving load tracer. But when you convert it to static loading, the loading value is considering not only fatigue load effect, but also dynamic load allowance factor as well. So loading value is showing different. So why is that? Because the purpose of moving tracer function is just to show you how the vehicle shape is and the location of the vehicle. It is not the value which are applied to analysis calculation. So if you want to see the actual value which are applied to the analysis, you need to convert it to static loading, and then you can see the actual value for the analysis. Okay. And in clause number 7.10, we need to consider load factors for the load combination. So different vehicle for the different limit state, we need to apply different load factor. So how we consider this load factor in MIDAS? So on the result menu, we have this load combination function here. And we can generate the load combination according to Australian standard automatically. So if you go to, on the load combinations menu, if you go to auto generation, we can select AS code here. If you click OK, all the load combinations will be generated automatically. So for the UDL, ultimate limit state, M1600 have 1.8 as load factor. Okay. So for the different vehicle, we have different load factor according to this table. Okay, move on to next. Deflection of superstructure. So for this clause, we need to consider M1600 moving traffic load without uniformly distributed load. So we need to have M1600 vehicle without UDF. So we have additional vehicle without UDF for M1600. This is to consider this deflection of superstructure clause. Okay. So move on to next. It is rail traffic. So we have added 300 LA design rail traffic load. So here we have the variable spacing between each axle group. Here, minimum 12 meter to 20 meter to give maximum effect in the member. So we need to decide the value of spacing for axle groups. And the number of axle group can be variable as well. So we need to find the critical spacing value and the critical number of axle group. And as we updated 300 LA rail traffic load vehicle, so you will find the critical number of axle group and the critical spacing as well. But in fact, it doesn't consider all the variable spacing for all each axle group. So it will not be like here we have 12 meters for spacing, here 30 meter, here 15 meter, here 20 meter. It won't be like that. It will be same value for all spacing. So it can be 30 meters for all the spacing or 12 meters for all the spacing like this. Because when I talked about this matter with Australian engineers, most people don't really care about all the various spacing. Normally, people practically apply the same spacing value for all the axle groups. So we implemented this feature in the same way. We can actually consider all the variable spacing, but then it will be too much calculation and it takes too long time to perform analysis. So we just we wanted to be more practical purpose to consider rail traffic load. So we apply one variable spacing value. And here we have option. You can decide how detailed consider the spacing value. So it will consider minimum 12 meter and maximum 20 meters as spacing. And if we input 1 meter as increment of distance, then it will consider 12 meters, 30 meters, 40 meters, and etc. Up to 20 meters. If we input, let's say, 0.5 meters here, you will consider 12 meters, 12.5 meters, and 30 meters, 13.5 meters like this. So if you input a smaller value, the analysis will be more detailed and it will take much more analysis time. Okay, so default value is 1 meter. So it will compare the cases from 12 meters to 20 meters by 1 meter. Okay, we also implemented a 150 LA vehicle to consider light rail traffic design load in the same way. And just like lane factor for road traffic load, so we have multiple track factor for ray bridges. So it is very similar. So most critical lane, we apply 1, and second, 1 as well. And for third lane, we apply 1 for 2 tracks and 1.85 for the third track, and so on. So if you consider ray traffic load, and when you define moving load case, you can select here ray traffic load, then you will consider multiple track factor, not the lane factor. It will be considered in the exactly the same way with the lane factor, and it can be shown in detailed report as well. And again, it shows distance between group. This is the most critical spacing value between the axis group. And move on to next. When it comes to rail traffic, there's one thing different from road traffic load, which is about dynamic load allowance. So it says the dynamic load allowance for shear, torsion, and reactions shall be taken as 0.67 of the value for bending moment. So we need to apply different value of dynamic load allowance factor for different forces, for bending moment and shear and torsion and so on. So here we have, sorry, input dialog here, we can input different dynamic load allowance factor for bending moment and all other effects, which is representing shear and torsion. So we can consider this as well. And move on to next. This is about assessment for existing bridges. We updated T44 turret load. Here we have also variable spacing. We consider this as well for T44 turret load. And it show you the critical spacing value and lane factor when you see the moving tracing function. And we have F44 as well. Here you can use this vehicle in the exactly same way. When it comes to the long bridge, a very, very long bridge, when loaded length is over than 150 meter, the loaded value, loading value can be lower than this 12.5 kilonewton per meter, but it doesn't tell you how it decreases along the meters and so on. So we leave it as manual input. So when it comes to over than 150 loaded lane, you can input a manual value here. Then you consider all the cases, gives you the critical case. And this is actually all for updated features. I'll tell you about additional options. So if you go to analysis menu and find moving load analysis control data, here we have option to choose between influence line, dependent point, or all point option. I'll tell you with an example. So let's say we have inputted M1600 vehicle without UDA, and I use influence line dependent point option here and see the result. And here's another result when I used here all point option. It shows difference. Before I'll tell you the differences between two options, I'll tell you about these values. So up here, this is showing the vehicle location when you see the moving load tracer. And this value down here is showing the actual load value when you convert moving load to static load. So this is the actual load value for the analysis. Okay. Again, moving tracer display doesn't show the vehicle for analysis. It is just showing just roughly the vehicle type and the location of the vehicle. So it is showing different. So, and I'll tell you the differences between two options. So when you use this influence line dependent point, you apply the axle loadings of the vehicle as many as where influence sign shows positive. So this is influence line analysis result. So when you want to see the maximum bending moment, then you apply the loadings to only positive area of influence line. But when you apply all point, you will apply all the axle loading to the loading area. So it doesn't consider the influence line result is positive or negative value. So you apply all the vehicles anyway. But in this example, it is showing only 6 vehicles, 1, 2, 3, 4, 5, 6. It is here. 1, 2, 3, 4, 5, 6. As I mentioned, for all point option, you apply. It's supposed to be applying all the axle load, but from axle load number 7 to 12, it is not showing here because as it consider infinite spacing, these axes are outside of the bridge. So that's why it is not showing in the result view. So it is not like if it is not infinite spacing, so you apply like this, all the vehicles when you use all point. This is one difference. This is the difference between two options. Okay, and we have concurrent force option. I'll tell you about this option with an example as well. So this is example analysis result. So for key element, element number 702, I want to see Fx, which is actual force, and it is showing 1,600 something kilonewton. And next, for the same element, when I see Fy, which is shear force, it is showing 100 kilonewton. And for same key element, when I see Fz, which is shear, for the minus axis, we have major axis, we have 600 kilonewton. And torsion and bending moment for the major axis and bending moment for the minor axis, we have result here. But as you can see here, for the same key element, it is showing different location. But sometimes we need to see when the bending moment shows the maximum, under the same location of the vehicle, we want to see sometimes actual forces, shear forces, and so on. So how we check that? So if you go to result tables and beam and force, for key element 702, it is showing maximum values here, maximum result. It is all from different location of the vehicle. If you want to see the concurrent forces effect, you can click right button and go to view by max value item and select the load cases, then we will see this table. So red rectangle is showing the maximum value here, like this. So it is showing the same maximum value, and other values are showing concurrent forces. For example, for this value, so when actual force is showing the maximum, under the same location of the vehicle, it is showing bending moment value. Okay, so this is useful option to design the bridge.